Okay, welcome to Lecture 3, Video Lecture 3, or ECE 203. In this lecture, we're going to talk about how we can add sinusoids of the same frequency. Okay, so last time we looked at plotting simple sinusoids, and just given a sinusoidal function of just one term, just the cosine of the single frequency, how we could go about plotting that. And what I want to talk about in detail today is how we can use complex representations to add sinusoids of the same frequency. So what I have written here is just an example of a sinusoid. You can see there's three terms here. Okay, this first term, the 7 cosine 2 pi times 5t plus pi over 2. Of course, the frequency here is f equals, of this particular term, is 5 hertz, right? So this is a sinusoid frequency of 5 hertz. You also notice that the second term is also a sinusoid with the frequency of 5 hertz. Right? Just underline both of those. The last term, on the other hand, is not a sinusoid at 5 hertz. It's actually at 3 hertz. So we're adding two sinusoids with the same frequency and one sinusoid of a different frequency. And the actual plot of this is shown on the screen below. You can see there's some kind of periodic nature. You could see how you could potentially add up some sinusoids and get a signal like this. So what I want everyone to note is that we can actually combine these first two terms. Okay? So the sinusoids that are at the same frequency, we can combine into a single term, right? And that term is actually this one right here. Okay? And we'll go through exactly how to do that in this lecture. Before we look at how we can add cosines of the same frequency, let's just look at how phase affects how we plot sinusoids. So if you remember from last time, one of the first things you do is you look at the amplitude of the sinusoid. So in this case, the amplitude is just going to be 1. So the first thing I would do is denote that on the plot. So I'd say there's plus 1. We know that this sinusoid, the maximum value, is going to be at plus 1, and we know the minimum value is going to be at minus 1. Okay, so to see how phase affects things, consider the following. If what I'm underlining in blue here, if that equals 0, then the cosine should take on its maximum value, right? Because cosine of 0 is, of course, equal to 1. Okay, and that's as big as the cosine gets. So if 2 pi f naught t plus phi, if that equals 0, then that means that cosine of 2 pi f naught t plus phi equals 1. Okay, so back to this equation that I just drew. Let's just solve that for t. We do that, see, t, of course, equals minus phi divided by 2 pi f naught. And so what happens at this time? At this time, we know that cosine has a maximum value. So if we use the values phi equals pi over 3 and f naught equals 1, then this is just minus pi over 3 divided by 2 pi, right? Which should just get me 1 over 6, minus 1 over 6. Okay. So I come back up here, and now I'm just going to, since we haven't really labeled these axes, I'll just mark this point as minus 1 over 6. Okay. I know that cosine will hit a maximum there. And then I also know that the period, right, since f naught equals 1, we also know that t naught equals 1 over f naught, which equals 1. Right. So if I now were to label, let's say, maybe 5/6, let's just say that's at this point 5/6, then this difference between -1/6 and 5/6, that's a full period, right? So the cosine should make a full period here. Let me just try and draw that quickly. Right, we'd have something like this. Maybe another peak there. And again, you guys get the idea. It's my rough freehand drawing. I want to review complex numbers and Euler's identity. So you can see here we can represent a complex number, we'll just call that number x, as the sum of alpha plus j beta. Okay, so we'll refer to alpha. Alpha will be the real part of this complex number, and beta will refer to that as imaginary, the imaginary part. Right? And another notation we'll use is as follows. We'll say when we want to take the real part of the complex number x, we'll just write Re of x, and that's just going to be alpha, right? Okay, it's the part that's not multiplied by j, okay? Not multiplied by the imaginary number. Okay? Again, the imaginary part we'll just write as Im, right? Im of x, just going to be equal to beta, okay? It's the imaginary part of the complex number x. So again, j represents the square root of -1. And so we can plot an imaginary number in the complex plane, right? And that just means we draw two axes, the real axes, okay, that's the horizontal axes, and the imaginary axes. So we could put a point, this point x, let's just say, is right there. Call that x. All right, and in plotting that, the imaginary value here on this vertical axis, that's of course beta. And on the real axis, that's alpha. All right, so another way we could think about this number x is as a vector. Okay, so let's draw a vector starting at the origin out to x. Okay, and we can represent a complex number based on the magnitude, and that's the length of this vector, so we'll denote that r, and the angle theta, which is the angle that this this vector x makes with the real axis. Okay, so just from trig, we can say x, that's going to equal, well, alpha plus j beta, but let's write that in terms of r and theta. Okay, so x is going to equal r times the cosine of theta, okay, because that equals alpha, plus j times r times the sine of theta. Okay, and that's just trig, just basic trig, right? This distance is going to be r times the sine of theta, and this horizontal distance, that's r times the cosine of theta. Okay, so that's another way we can represent x. All right, now let's jump down and look at Euler's identity. Okay, so we got Euler's identity right there, and notice how we can now write the number x using Euler's identity in terms of complex exponentials. Okay? Just comparing these things should be pretty obvious that x is also equal to r times e to the j theta. Okay? So x equals r e to the j theta. So again, where r is this distance, or the magnitude of the complex number, and theta is the phase of the complex number. All right, so in general, when we have a complex number x, we can find the absolute value of x as the square root of x times x conjugate. We'll write it like that. And conjugate just means we put a minus sign in front of any imaginary, in front of any j's or i's that show up in the expression for x. Okay, so could write that as square root of alpha plus j beta. And now taking the conjugate, alpha minus j beta. Okay? And this, if you work this out, should just be, we should get some canceling here. We should just get the square root of alpha squared plus beta squared. And that, of course, equals r. Okay? That's the length of this vector. All right, so we have Euler's identity written down here. Okay, we just saw this briefly at the end of the last lecture, but Euler's identity now relates a lot of interesting things, right? It relates the natural number, so E is the natural number, it's 2.718. And the natural number raised to the imaginary unit times just a real number is equal to cosine theta plus j sine theta. That's Euler's identity. All right, so let's look at some real examples of how we can manipulate complex numbers. Okay, so the first example is just x equals 3 minus 4j. So just so to make sure we're all on the same page, if I write the real part of x, that just equals 3, right? Likewise, if I write imaginary part of x, that just equals minus 4. So let's say I want to write x in the form r times e to the j theta. How do I figure out what r and theta are? Well, first of all, r is termed the magnitude or the absolute value of the complex number. Okay, so sometimes that's just denoted as r equals absolute value of x. Okay, sometimes it's written abs of x. And really, it's a simple formula. Okay. In this case, we were to go back and look at the picture I had on the previous page. It's just a triangle. So you say that the hypotenuse of that triangle is just the square root of each side, the length of each side squared. Okay. So that, in this case, that just equals the square root of 3 squared plus 4 squared. Right? So that's going to equal 9, the square root of 9 plus 16, so it should just be the square root of 25, which is just 5, right? It's a 3, 4, 5 triangle. Okay. So more generally, if I don't have the complex number written in this nice form, this alpha plus j beta form, the absolute value of x is equal to the square root of x times x conjugate. Okay? Where conjugate means all I do is I take any place that there's a j and replace it with a minus j. Okay, so in our example here, that would just be the square root of the quantity 3 minus 4j, now times the conjugate of that quantity, which is 3 plus 4j. What you'll notice is that the cross terms cancel and we're just left with what we had above, and that equals 5. Okay. So the last thing that's left is theta, right? How do we find theta? That's called the absolute value, or excuse me, the phase or the angle of the complex number. So here all we would do is just again use simple trigonometry. And if you go back to the picture I had drawn on the previous page, theta is just always going to be equal to tangent inverse, okay, the arctangent of the quantity minus 4 over 3, right? Okay, and more generally, theta equals tangent inverse of the imaginary part of the complex number. Oops. Imaginary part of x divided by the real part of x. All right. So let me come back up here, and now we can just write this number as 5 e to the j theta, right? Where theta is just the inverse tangent of minus 4 over 3, right? You could just evaluate that on a calculator. So now this next example, this one we should be able to go through this one a lot quicker. Let's just try and get this in the form r e to the j theta. Well, we know from before we can write x as follows. X is just simply, now using the same theta that we had before, should be 5 times e to the j theta, where theta is defined right here. This quantity to the 5th, right? That should be the same as what we have written here. So that should be 5 to the 5th. E to the j times 5 times theta, right? We're just doing algebra here. Okay? And this now, again, is something I could just, once I had the value of the tangent, I could just evaluate that on a calculator. All right. So the last example I want to do is now just to remind you guys how we go back to this kind of rectangular form. Okay? If we had, for example, x equals 6 e to the j pi over 4. Well, we just use Euler's identity, right? Euler to the rescue. So here, using Euler's identity, this is just equal to 6. Okay? Now, times the quantity, cosine pi over 4 plus j sine pi over 4. All right. And then we're done. So if you didn't know what these are, you could just evaluate them again on your calculator. Okay? Or you could just draw a unit circle and figure them out. Okay, the next thing I want to do is quickly verify Euler's identity and show you guys where this comes from. Right? It seems pretty mysterious that all these different things play together, including the natural number, the imaginary number, and sines and cosines. How we can just equate them in this way. So this really just comes from a Taylor series expansion, if you remember that from calculus. So what a Taylor series expansion does is it just expands a function with an infinite number of derivatives around the origin. Okay, and we can write f of x then is equal to this. See this, the function itself evaluated at 0 plus the first derivative evaluated at 0 divided by 1 factorial times x, and that's added to the next term, which is the second derivative of f evaluated around 0 divided by 2 factorial times x squared, and so on. So you can just come up with the Taylor series for e to the x, cosine of x, and also for sine of x. And we're just going to relate these things to verify Euler's identity. So what I have written in blue right here is if we just look at the Taylor series expansion of e to the x and plug in x equals j theta. Okay? So all I did was plug in x equals j theta. And you'll see a bunch of things. Okay? It's exactly what we've done above, but now we have these terms involving, like this one, the quantity j times theta squared, the quantity j times theta cubed, quantity j times theta to the fourth. Well, remember that j squared that just equals square root of minus 1 squared. So that should just equal 1, or minus 1, sorry. Okay? So you can see that that term, we just got a minus sign here in this term. And so on. You could look at j cubed, j to the 4th. Okay, j cubed should just be minus j. J to the 4th should just be plus 1, and so on. So the next thing we want to do now is write out what cosine of theta plus j sine theta. And let's look at the first few terms in the Taylor series expansion. So the first one, let's just take this cosine term, okay, this one. So we get a 1 here. And then the next term, let's borrow from the sine. So j times the sine of theta, that first term should just be j times theta, right? Okay. And then let's go back. I'll say, so we've taken both this term, we just cross that out for bookkeeping, cross this one out for bookkeeping. Now let's take this term. Okay. Right, all I did was take this term here in the cosine. So now that one's there. There should be a 2 factorial. And then I would just keep going in this manner. Next I'd take this term from the sine. So we should have a minus quantity minus theta cubed, and that's got to be multiplied by j, right? Because there's this j in the sine. So that should give us minus j theta cubed over 3 factorial. And what you see is e to the j theta, then the Taylor series expansion is just equal to the Taylor series expansion of cosine theta plus j sine theta. Of course, there's a plus dot, dot, dot. Okay. So that's one way to verify Euler's identity. So what can we use this for? Well, before we talk about that, let's just really briefly look at what are called Euler's, sometimes called Euler's inverse identities. And that's just, they're relatively easy to verify. We can just write the cosine itself as what's written here. That's e to the j theta plus e to the minus j theta over 2. So how would we verify that? Well, we could just plug in Euler's identity. So plug in all of this stuff into here, and also into here, into the minus j theta. So what you get if you did that, first say e to the j theta, well that should just be cosine theta plus j sine theta. That's divided by 2. Oops, sorry, excuse me. Yep, that quantity is divided by 2. Draw this out a little longer. And then now this second term involving e to the minus j theta. So that should just be plus, again, cosine of minus theta plus j sine of minus theta. All right. You'll notice that cosine of theta, that's actually equal to cosine of minus theta. So this term and this term are equal. Remind yourself of that. Just one thing, the cosine is an even function, but you can also just draw a picture of the unit circle and convince yourself of that. But it turns out that sine of minus theta, that equals, just write this, sine of minus theta, that equals minus sine theta. Okay? So these two terms actually cancel each other out. Right? And you're just left with 2 cosine theta, of course divided by 2. Right? So just cosine theta. Right. What's going to be more useful for adding exponentials is the formula that I have written here. So just by looking at Euler's identity, if we take the real part of it, we just get cosine of theta, right? Because remember, by taking the real part, we just cross out anything that's multiplied by j. Right? So the real part of e to the j theta, that's just cosine of theta. Let's see how we can use that to add cosines. All right. So let's say we have some number of sinusoids, and they all have the same frequency, right? So they all have frequency omega naught. That's the key here. Omega naught is the same in each term in this sum. Since we can write this sum as just the sum of the real part, okay, so what happens here is just that what I showed you on the last slide, that Euler's identity, we can write this cosine as the real part of a complex exponential. So of course we can write the sum of a bunch of cosines as the sum of a bunch of the real parts of complex exponentials. So now the next step, this one here, you have to convince yourself that the sum of a bunch of the real part of a bunch of complex numbers is just equal to the real part of the sum. Okay? That we can indeed take this real part out. And that might take some time to think about it. Maybe it's easier to see on the next page with a simple example. All right, so we're almost there. So now we have each term involving complex exponential. Right? Each one has some different phase, but they have some common frequency. So this term that I'm underlining can of course write as just e to the j omega naught t times e to the j phi k, right? For each term in that sum. So we can just factor this term out then. Right? And that's exactly what I've done here. It's been factored out. And so now it's factored out of the sum. And now we really just have a sum of a bunch of complex numbers, right? This is just expressed in that radial or that polar form. Okay? So it's just think of it as a sum of a bunch of vectors in the complex plane. This portion is really just another complex number, right? And so let's just generically we can call that complex number a times e to the j phi, right? Okay. So that's how we can add sinusoids with the same frequency. So it's just kind of a general fact now that if we have a bunch of sinusoids, they can all have different phases, but if they all have the same frequency, we can just combine them and write them as a single sinusoid. So that was the key takeaway here. Bunch of sinusoids with the same frequency, even though they might have different phases and different amplitudes, we can write them as a single sinusoid. All right, let's see an actual example of this. And this is the same, this is the first two terms in the sinusoid that I showed you guys on the first page of notes for this slide. So we have two terms, right? Again, circle, you can see the frequency is the same, right? The frequency is 5 hertz for each of these sinusoids. And of course they have different phases. One is pi over 2, the other is minus pi over 3, and the amplitudes are different. So how would we proceed here? Well, we could write this first term. That just equals, using Euler's identity, the real part of a complex exponential, right? In particular, j times 2 pi times 5 plus pi over 2. Then we could write the second one in the same way. That's actually, it's written right here. So those two things should be the same. Right? We've just rewritten this first line using the real part of complex exponentials. All right, so the next thing that happens is now I've taken this, you see there's a real here and a real here, and if we're just taking the real part of two complex numbers and adding that together, that's the same as just taking the real part of those two complex numbers after we've added them together. So that's this next step. Okay? So now you see there's one real of that whole quantity. And then in this following line, then I've factored out the terms involving the frequency, e to the j 2 pi times 5t. See that here and here. They get factored out to here. And then this second term, right, this is just a complex number. Okay, so the way I would figure out what the amplitude and the phase of this complex number is, I would just plot both of these things in the complex plane, right? Just like we saw about 3 pages back. Alternatively, if you just had MATLAB open in front of you, you could just write this line in MATLAB and then type ABS, and that will give you the absolute value, and you could type phase, and you'd also get the phase. So you'd see the absolute value would be 8.79 and the phase would be 1.68. Okay. So then we just continue in this manner. And again, we have the term involving the frequency factored out, the term, this complex number written here, and then we can just take out 8.79. That's just the scalar that multiplies this complex exponential. We can bring that out of the real part. And this, of course, right, that's just Euler's identity again for what we've seen a bunch of times is that we can write this cosine as the real part of a complex exponential. So let me just open up this code. And the code that I'm showing you here now is just going to plot the sinusoids that we saw on the first slide of lecture. So that I'm just highlighting right here. Okay, you can see there's 2 different cosines. These are both of the same frequency. These are both at 5 hertz. And then there's also this last one that's at 3 hertz. Okay, so we'll be able to combine, we did just combine these two. And now we're gonna plot this first expression, and then we're gonna come down here, and the expression we just derived that involved 8.79 and a phase of 1.68 radians, we're going to use that instead, and we'll see that indeed these plots are the same. Okay, so let me run this. Let me minimize this second figure for now. But sure enough, you can see this first plot in blue is the 3 different cosines added together. This lower plot is just the 2 cosines added together, where we've combined the 2 cosines with the same frequencies. All right. So the second plot that I showed, just run this again, does the following. It's just, we're going to further break this down. It's going to show you guys how, okay, here's the first cosine, that's this term here, and then the second cosine, that's this term right here. When those get added together, which we'll call x34, when those get added together, it's just another cosine of the same frequency. So let me run that again. Okay, so here's the second figure. You can see this first one, that corresponds to 7 cosine times 2 pi times 5, right? It's just a cosine frequency of 5 hertz. The second line, the amplitude is minus 2, or excuse me, 2, and the frequency again is 5 hertz. And so then those are added together in this line, and that just gives you yet another cosine at the same frequency. It's pretty easy to check just visually that these all have the same frequency.